So dear students, finally we have reached the last topic in our syllabus in module number 4, that is the Joule-Thomson expansion or the Joule-Thomson effect. We have discussed the Joule phenomenon or the Joule effect in our previous modules, whereby we have seen that you are able to cool down gases by making the gas to undergo an adiabatic free expansion, and we have seen that an adiabatic free expansion is happening at constant internal energy. Now, in the case of Joule-Thomson expansion, which is quite similar in the name, but see that there are some differences as well. We will see that this is yet another way to lower the temperature of a gas. So when you learn the history of thermodynamics regarding obtaining low temperature systems, earlier it was thought that air is remaining in the gaseous state at all temperatures, and gases like oxygen, hydrogen, nitrogen, helium, etc. were considered as permanent gases. But later on, the studies on the effect of pressure and temperature on the volume of gases showed that the liquid and gases are only two stages of a long and continuous series of physical changes that can happen for a system. It means that the gases which were considered to be permanent gases can actually undergo a transition to liquid state under proper conditions of pressure and temperature. And these studies were taken forward by a number of physicists, including James Prescott Joule and William Thomson, otherwise known as Lord Kelvin, and also physicists like many other physicists like Linde, and it was by the experiments done by Joule and Thomson which finally established that whenever a gas is undergoing throttling process, we have already discussed about throttling process in the same module itself. Whenever gases undergo throttling process under proper conditions, their temperature will be getting reduced, or there will be a lowering of temperature. And this particular phenomena, in which there is a change in temperature, the change need not be always lowering of the temperature, it can be a rise in the temperature. The phenomenon of change in temperature of a gas as a result of sudden pressure change over a valve or a throttle is what is known as Joule-Thomson effect or Joule-Thomson expansion. So there are several names for the same experiment or for the same phenomena. Either it is Joule-Thomson effect or Joule-Kelvin effect. The reason you can understand, because William Thomson is also known as Lord Kelvin. So it's Joule-Kelvin effect, or it's it was performed by using a porous plug. So it's also known as porous plug experiment or porous plug process or the throttling process. So all these phenomena, all these names are representing one and the same effect. Okay, so basically this is the thing. Suppose that you maintain a gas. Okay, so you can see the adjacent figure which I have reproduced from the previous discussion. So if you have a sample of gas kept under a constant pressure, say Pi, and there is some sort of a porous plug. So this is a porous plug. You know, a porous plug consists of a large number of fine pores through which the gas molecules can pass, and it will undergo a sudden expansion. Okay, to the other region where there is another constant pressure PF. So PI and PF are the two constant pressures, with the condition is that PI is greater than PF. So the gas is going from a high pressure region to a low pressure region. So that is something very, very important. Okay, so the gas must be flowing from a high pressure region to a low pressure region, with the condition that both PI and PF are remaining constant throughout the process. So PI and PF are constant pressure such that PI is always greater than PF. We have seen in the previous explanation how that is maintained. Okay, so what will happen is that the gas will be always undergoing some change in temperature. So depending on the nature of the gas, or depending on the initial temperature of the gas to begin with, either there will be an increase in the temperature or there will be a decrease in the temperature. Okay, so that is something to be careful about. So as a result of the Joule-Thomson expansion, the temperature of the gas may increase, it may decrease, or in some cases, some special cases, there won't be any change in the temperature, constant. So there are three possibilities, okay, as a result of the Joule-Thomson expansion. And the thing to be noted is that as we have discussed, the throttling process was discussed in our previous topic as an example of isenthalpic process. As an example of isenthalpic process. Or you remember that that was our conclusion, is it not? At the beginning of the throttling process and at the end of the throttling process, the quantity which remains constant is nothing but enthalpy. So we have proved that H initial is equal to H final, is it not? Okay, so we can say that the Joule-Thomson expansion basically is a process which happens at constant enthalpy. So it is regarded as an isenthalpic process. And this phenomenon, after its discovery in the year 1852, so you can just see that it was in the half of or the middle of 19th century, has become the basic working principle behind most of the refrigeration systems, the liquefiers, because in many cases we want to liquefy gases. So what we do is that we will be applying a series of Joule-Thomson expansions, okay, which is known as regenerative cooling. That is actually the technique that is known, okay, regenerative cooling techniques. So whereas there will be some sort of pre-cooling. So from room temperature, the gas will be first pre-cooled to a particular temperature below its what is known as inversion temperature and all, and then it will be made to undergo what is known as Joule-Thomson expansion. So this is a technique used in liquefiers. It is also used in heat pumps by using some compressors. Okay, pressure will be increased, then it will be made to undergo sudden expansion, and heat pumps and such things like air conditioners and all. So remember that this phenomenon has become so widely used, or it has now got far-reaching consequences or far-reaching implications in many of the thermodynamical systems. Okay, hence the most common application or the use of Joule-Thomson expansion nowadays is in the liquefaction of gases. As I told you in the beginning, that those gases which were thought to be permanently gas, okay, were later found to be liquefiable. Okay, so by properly controlling the pressure and volume of these gases, we can liquefy them. Okay, so we are very familiar with liquid nitrogen. We have heard of that, okay, liquid nitrogen or liquid helium. So helium is having some peculiar properties whereby it attracted the experimentalists for a long time. So liquefaction of old gases. So almost all the gases we are able to liquefy by time by applying pressure and making it undergo Joule-Thomson expansion. So liquefaction of gases or production of low temperature. There are a number of phenomena where we need to attain very low temperatures. Okay, so maybe you know that the low temperature physics has got a particular name. There are a lot of experiments that is happening at low temperatures because at low temperatures the properties of many substances will be showing drastic changes. So the branch of physics or thermodynamics in particular, which deals with the low temperature, is known as cryogenics. You might have heard of this word, cryogenics. Okay, especially our space program, they depend a lot on cryogenic engines. Okay, fuels, etc. So we have produced, or we have developed our own indigenously developed cryogenic engines, and that was actually a hurdle in development of our space programs and all. Okay, so just I wanted to mention that production of low temperatures have become now very easy by the application of the Joule-Thomson expansion. Okay, so another important point to note regarding this phenomenon is that the extent of cooling, how much the particular gas sample can be cooled, it depends on many factors such as the nature of the fluid, nature of the particular gas. See, depending on the nature of the gas, by the nature of the gas I mean the nature of the intermolecular force of attraction. Okay, because the phenomenon has got a dependence on the type of molecular forces that exist in the gas. Similarly, the difference in pressure on both sides of the throttle. Okay, so on the valve, I had told you that we assume that the initial pressure is Pi and the final pressure is Pf. So let me say that the difference in pressure between the two, let me say that is some delta P. Okay, there will be some finite difference in pressure that is maintained on both sides of the. So depending on delta P, the amount of cooling will be different. So more or higher the difference in pressure across that valve, higher will be the cooling effect. That is that. Okay, and also the extent of cooling will depend upon the initial temperature. Initial temperature means the temperature at which the gas is made to undergo expansion. Okay, so for example, you can take the gas at room temperature and you just make it to undergo throttling through a porous plug. Okay, so sometimes you may not experience any sort of cooling. Okay, so there is a particular temperature for Joule-Thomson effect to happen. There is a minimum temperature, there is a threshold temperature only below which only Joule-Thomson effect will occur, and that temperature we will see later. We will define it also. That temperature is known as inversion temperature, and we will see that for the Joule-Thomson effect to happen, that initial temperature of the gas should be below its inversion temperature. That's why I told you that usually in order to make use of Joule-Thomson effect, the gases should be pre-cooled. Okay, so that it is brought below its inversion temperature, and then we will apply Joule-Thomson effect so that it can be liquefied very easily. Okay, and one particular thing to note, keep in mind, is that Joule-Thomson expansion is not shown by ideal gases, and that's a very important point to be kept in mind. I don't know whether you remember, we have seen that the Joule expansion, which we discussed earlier, Joule expansion and the Joule coefficient, we have already discussed in one of our modules. I think it was in the second module we discussed about the Joule expansion, whereby we have seen that even ideal gases are showing Joule expansion, okay, or cooling effect on Joule expansion. Unlike Joule expansion, the Joule-Thomson expansion, which is an isenthalpic process, cooling effect will not be observed in the case of ideal gas. Or I can say that, or we can conclude that ideal gases are an exemption to the Joule-Thomson expansion. Okay, and hence we can use the porous plug experiment to determine or to test the nature of a given gas. Means you can just check whether the given gas is showing perfect gas behavior or not, or to what extent the given gas sample is ideal or not, perfect or not. So that is yet another application of what you can say that the Joule-Thomson expansion. So that is quite an introduction to the phenomenon of Joule-Thomson expansion. So what I want to tell you is that there are a large number of techniques used to liquefy gases or used for production of low temperature. One common technique being the adiabatic expansion. You know, adiabatic expansion results in cooling because work will be done at the expense of the internal energy. Now we introduce Joule-Thomson expansion or the throttling process as yet another method to produce low temperature, and takeaway is that This is the basic working principle behind producing low temperatures in industries, mainly in the liquefaction of gases. Okay, so we'll discuss about the thermodynamical relevance or the mathematics behind this particular phenomenon in the next session. Okay, thank you.